Okay, just to remind you what we're doing is we want to do polynomial identity testing. I give you some algebraic expression, and you want to know is it 0 or not. And I talked yesterday about sparse polynomials, about depth repowering, and reruns algebraic branching programs. Today I want to say a slightly different paradigm, reviewing some of the models that I talked about yesterday, but just doing sort of something slightly different. Okay, so I'm going to sort of tell you like what this framework is. It's involving taking a polynomial and translating it in some way, and then arguing that there are monomials that involve few variables, which is similar to what we did yesterday for depth repowering. And then I want to instantiate that with sparse polynomials, which is sort of a simple example of this, and then talk about something called a commutative reruns ABP, which I'll define. Okay, so the main actor for today is the following set. Okay, so it's going to be P sub L. And P sub L, right, is going to be a set of polynomials. As always, I'm going to have n-varied polynomials of degree at most d. And this is going to be, P sub L is defined to be the following set of polynomials. So f is going to be polynomials f, where if you expand them out, where you expand it out in this monomial representation, I want to say that there's some monomial which I really like, which is friendly, right? So it's going to be a set of polynomials such that if f is non-zero, so there's the zero polynomial in P sub L, but there's non-zero ones, and if it's non-zero, then this implies that there's some coefficient which is non-zero, where the monomial associated with this coefficient is special. In particular, what I'll call L0 norm is at most L. So what I mean by the L0 norm, this is just the number of non-zero entries in this exponent vector, right? This monomial involves n variables potentially, but I'm saying that there's some coefficient that only involves L variables. Okay, and so such monomials I'm going to call small support in the sense that their exponent vectors have small support, and these are sort of the main actors, the main actor for today. Okay, so to remind you what happened yesterday, right? There was this theorem that said the following. So suppose that you have one of these depth repowering things. The definition is not important for right now, but this class is contained in, what we proved is that these expressions, if they're non-zero, always have a small support monomial, right? And what was the support? It was order log s times d. Okay, so this was some structural result we proved yesterday. And then how did we use this to get identity testing? Right? There was just this fact, which is that P sub L has a hitting set of size nd to the L, or something like that, approximately, right? And so in this particular, if you combine these two things, you get a hitting set for depth repowering, right? And so the main question is, how can we use this idea for other classes? Okay. The challenge seems to be that P sub L, when L is polylogarithmic, seems pretty weak in the sense that if you just consider the monomial x1 times x2 dot xn, it's not in P sub L for any L less than n. So that seems like there are very simple things outside P sub L. So it seems like this fact may be largely irrelevant, but I want to tell you it's not, right? And so what's the basic lemma? Suppose f is non-zero, then if you take a random alpha, okay, and what you're going to do is you're going to translate f with alpha. Okay, so if you take a random alpha, then f of x plus alpha is in P sub 0. Okay, so you pick a random alpha, and what does this statement really mean? What this statement is saying is that the constant term in this expression is non-zero. And if you parse that for a moment, this is equivalent to saying that f of alpha is non-zero. Right, so we showed yesterday the Schwarz-Zippel lemma, right, saying that if you pick a random point, the evaluation is non-zero with high probability. And so equivalently, you can say the translation is in P sub 0. Okay, so this is sort of a fancy way of saying something stupid, but I want to say that this is an insightful lemma because of the following idea. Okay, so this is due to Agrawal-Saha-Saxena, which is basically, can we de-randomize this? right? In the sense that this is saying for a random alpha, which is very computationally expensive from the perspective of randomness, that we can get it into p sub 0. But maybe what we could do is we could use sort of a pseudo-random alpha, and maybe not place the polynomial in p sub 0, but place it in p sub polylog. Okay? And then once you do that, you can use the hitting set for that, for p sub l. Okay? So what does that really mean? Suppose you have a class C, right? This is some class of polynomials, and varied degree at most d, something like depth repowering or commutative, or maybe V1 CDPs or sparse polynomials or whatever. What we want to do is we want to find some h, which it's not really hitting set in this case, but I'm going to use the same thing. It says that for all f in C, if f is not 0, then there's some translation in H that puts you in some p sub l. Right? There exists some alpha in H such that f of x plus alpha is in p sub small. So, I mean, small depends on exactly how it goes. But basically, if you have this situation, then this is, it's still a polynomial in X. It's in p sub small, and then you apply your thing here. Okay. Now, I'm not going to exactly do it this way, because what we talked about yesterday, there's hitting sets and there's generators. So there's another version of this, the sort of the generator version. And how does that go? Well, you want a map G, which is going to take a small seed length, and so this is going to be some small seed length thing which maps you to n things, and this is going to be a polynomial map as before, where we want the same thing. We want that, for all f in C, if f is non-zero, then if you translate f of x by your generator, this is in p sub small. So let's just parse this for a moment here. What you're doing here, like here you translated by a vector of scalars. Here you're translating by a vector of polynomials. So when I'm saying this is in p sub small, this is a polynomial. I'm treating this as a polynomial where the y's are sort of in as coefficients. So this is still a polynomial in x whose coefficients are polynomials in y. And in that case, you can then talk about, when I'm saying the monomial is non-zero, it's non-zero as a polynomial in y. Okay? And so just how hitting sets and generators were equivalent before, these two perspectives are basically the same. The generator one is, as before, sort of somewhat more robust. And how do you sort of encode this robustness? It's basically that, suppose that f of x plus g sub l, or g sub y, g of y, and g of x plus g of y. Suppose you've translated both of them into p sub l, right? Then if you take their multiplication, how does that go? Like, what can we say about how it's contained in one of these things? This should be contained in p sub 2l, right? That's not too hard to see. With the hitting set, it's not. You really can't do that because, for the same reasons that hitting sets don't work on a multiplication, as I showed yesterday. Okay, but I think that to some extent the main question in this approach is how do you handle f plus g? Okay, and it's sort of the same question as before, right? We saw yesterday that if you have a generator for a class C, you have a generator for class C times C, but it doesn't mean that you have a generator for C plus C, right? So there's this question, how do you handle additions? And this is sort of non-trivial. And basically what you have to do is you have to use ideas, and the main idea here is to use some sort of complexity measure and do something with that. Okay, so yes. Okay, so now I want to talk about sparse polynomials and how to implement sort of this approach for sparse polynomials. Okay, just to remind you, what does that mean? Right, we have f of x, and we expand it as a summation of s monomials, and this is an s sparse polynomial. Right, and we saw sort of this combinatorial identity test yesterday based on sort of hashing. Right, and I want to give a more algebraic hitting set today based on these sorts of ideas. Okay, and it'll be something somewhat similar, simple. So the theorem here, there are two proofs. One is due to Rohit, Arpita, Nitin, and Thomas Thurv, and another proof is due to me. And I want to tell you how to translate this into small support. And so both of what's going on here is that if f of x is as sparse, then suppose that you translate f by the single vector 1. Okay, so it's the all ones vector. Then this is in p sub log s. Okay, so here our h, we're not really using a generator in this case, but like you just have a single vector, you're translating by this single vector, and you automatically get something which is a very low support, which is log s. Okay, and so that would give you, by appealing to this fact, a quasi-polynomial size hitting set for sparse polynomials. Obviously, this is worse than what we saw yesterday. Yesterday we saw polynomial size, but this has some advantages because in these two works they sort of take this in different directions and do even more things that you couldn't do with this combinatorial approach we saw yesterday. Okay, so how does the proof go? Well, there's really two steps, and this is going to mirror what happened for the step repowering that I showed yesterday. Okay, so the first step is to get a lower bound. Okay, and then the second step is to make this lower bound robust. Okay. And then once we make it robust, this structural result will hold in the same way that we proved this structural result yesterday by having a lower bound and making it robust. And then, of course, you get the hidden set. Okay, so what is the lower bound? Okay, so the lower bound is kind of stupid. Bear with me. The lower bound is as follows. Consider the following polynomial. You have x1 plus 1 times x2 plus 1 dot dot xn times 1. This requires 2 to the n monomials. Right? If you express it out in its dense representation, there are 2 to the n monomials. This is obviously true, right? But I want to prove it to you in a way which makes the robust step possible. Okay, so how are we going to prove that? Well, it's basically the following magical thing out of a hat. Okay, so yesterday when we were proving this theorem, right, we saw this partial derivative measure. Right? You have an f and you take its partial derivatives. The problem is you can't really use just partial derivatives here because this is basically like a monomial but in a translated basis. And as we saw yesterday, monomials have a large partial derivative space. So we need some measure which is sensitive to the basis you're working in. It needs to be small for some monomials, and it needs to be large for translated monomials. Okay? And so the magic operation here is the following augmented thing, which is as follows. You're going to take f, you're going to take a partial derivative with respect to some monomial, and then you're going to multiply by that same monomial. Okay, so just to remind you what my funky notation means, you take this partial derivative, right? So you differentiate x1 b1 times, and you differentiate xn bn times. That's your derivative, and you have this order derivative in the top. And then you're going to multiply by the monomial xi to the bi. Okay, so there's this correlation between the derivative you're taking and this monomial you're multiplying by. And just to foreshadow what's going on, what Chandan is going to talk about is more general differential operators here where you may or may not have correlation like this. Okay, but this is the main operator that we're going to use. And why is this interesting? Right? What happens when you do this to monomial x to the a? Right? So what are you going to get? Well, you're first going to differentiate, and what's going to happen to the different? And you're going to get something like x to the b times the differential here. And what is that going to be? Well, if you sort of do it out, it's going to be, okay, so I do derivatives slightly differently. So this is a Hasse derivative, but it doesn't really matter. Okay, so basically it's going to be some scalar. In this case, it'll be the binomial coefficient a choose b, which is the product of ai choose bi. Doesn't really matter, but basically it's some scalar times x to the a minus b. Right, so this is you take the derivative, and every time you lower the appropriate power, and then some scalar pops out. The scalar may be 0, it may be non-zero, but the point is that because you multiply by this monomial back, this is equal to a scalar times x to the a. Okay, so what this is saying is that you take this operator on a monomial like this, and you basically get something which is the same, right? But what happens when you have a translated monomial? Okay, so what is this thing? This is just the product of xi plus 1 to the bi. So this is the vector of all ones. Okay, what happens when you do this map? Well, what you're going to get is, this a choose b, x to the b, x plus 1 to the a minus b. Okay, which is different than what you had to begin with in a non-trivial solution A. Okay, and the point here is that these polynomials, assuming the scalar is non-zero, are linearly independent. So these are linearly independent for whenever you have b at most a. So this is a vector-wise comparison. Whenever you differentiate something, and this thing is not zero, these polynomials are always linearly independent. Okay, and so that's basically suggesting that what the complexity measure should be, right? We take all operators of this form, apply it to our polynomial, and measure dimension, right? Okay, so the mu here is going to be defined as the dimension of all of these these differential operators as we arrange over all possible b. Okay, so then just to recap, like what happened is that if you take a monomial x to the a, right, this measure is 1. Because when we're measuring dimension, these scalars don't really matter. Okay, and then if you have mu on S sparse polynomials, right, because we're doing everything with linear algebra is magical, right, so this is subadditive, so the measure should be at most S. Yeah, okay. But the key insight is like what happens when you apply it to monomials in this translated basis. And basically, as I already argued, this measure should be large. Okay, and so because the measure is large, it basically is concluding the lower bound, right? So the measure of x plus 1 to the 1, which is my notation for this monomial, this is equal to 2 to the n, right? Because that's the number of exponent vectors that are less than b, right? Okay, so that's basically saying that this monomial requires this many monomials, right? That's a very convoluted proof. I'll apologize, but the reason we're doing it is because we're going to get something more, right? So how do we make it robust? Okay, so what we saw last time with depth-3 powering is that we took this monomial lower bound, that monomial requires exponential sizes depth-3 powering, and then we translated it, or we made it robust into a leading monomial lower bound, that the number of variables in the leading monomial is logarithmic in the size of the formula. So let's see what happens when we do this translation to things like leading monomials. Right, we have x1 to xn, and then we do this translation with this vector 1, and we get this polynomial that we just considered. And what is the leading monomial of these two expressions? Well, there's only one monomial here. It's very clear. It's just the same thing. But if we look at this expression, the leading monomial is the same. It's still x1 up to xn. Okay, so this seems to suggest that the leading monomial approach doesn't work. Okay, and so when something doesn't work, what do? You do it anyways. Okay, and so the main thing that you have to do here is stand upside down. Okay, so instead of leading from the front, you lead from behind. Right? So let's look at the trailing monomial, the one that is the least with respect to this lexicographic ordering. Well, again, there's only one monomial here, right? But when you go to this right-hand side, the translated version, now you have 1. Right? So this is saying something very interesting, that translation does not affect the leading monomial, but it affects the trailing monomial heavily, especially in this example. So what we want to do is, instead of saying that the leading monomial involves few variables, we want to say that the trailing monomial involves few variables. Okay, and that's basically, that's what we want, right? That the trailing monomial of f of x plus 1 involves order log s variables, right? Whenever this thing is S sparse. Right, so I took my sparse polynomial, I translated it, the number of variables in trailing monomial is small. Okay, and that is that implies this theorem here, right? Because the trailing monomial is a monomial, right? And this is saying that, there's some monomial with non-zero coefficient that involves log s variables, and that's exactly the structural result. You can take the structural result, you apply a hitting set, and then you get your PID that way. Okay, so what we want to do is we want to prove this using this set of differential operators. I'm going to use a slightly different measure. It's called mu prime, which is as follows. Because this measure was tuned to the fact that it's sparse in the normal basis. Okay, but what I want to say is that now we're considering something which is sparse in the translated basis. So I need to translate my operators here. Okay, and it turns out that when you take derivatives are basically translation invariant, but these monomials are not translation invariant. So the measure here that we're going to use is the dimension of the following operators. You take a monomial in your translated basis, some x plus 1 to the b. You multiply it by the derivative of f in x to the b. Okay, and this is basically the translated version of that measure there, right? So if f is sparse and you translate it, then basically by the same proof, you get that f of x plus 1, the measure mu prime here is s, for the same reason as it was before. Okay, and now what we need to say is that if a polynomial has a trailing monomial with many variables, then the measure is large. And that would, by invoking this bound, would say that the number of variables in the trailing monomial is small. Right? So what do? We'll consider the trailing monomial of one of these operators applied to f. Okay, so you have x plus 1 to the b, you take a derivative of x to the b, and you have f. Okay, now, fun fact, the trailing monomial has this nice homomorphism property with respect to multiplication. Okay, so the lemma here is that the trailing monomial of f times g is the trailing monomial of f times the trailing monomial of g. This isn't really not too hard to see. I'm not going to prove it for you, but it's basically that the trailing monomial is in some sense extremal, and so if you multiply two polynomials, there can be no cancellation at the extremes. And this is very analogous to the fact that if you take two degree d polynomials and you multiply them, the product is degree 2d. Okay, and the leading monomial is also multiplicative with respect to homomorphism, but basically using these homomorphisms is what makes this all possible. Okay, so that's one lemma about the homomorphisms of trailing monomials, but we also saw something homomorphism with leading monomials yesterday with respect to derivatives. And the same thing will hold with trailing monomials. So the lemma is that if you take a trailing monomial of a derivative of a polynomial, right? How can we understand this? And it's the same thing that happened yesterday. You can basically interchange the order of operations. This is equal to the derivative of the trailing monomial of f most of the time. This is true only if this derivative is non-zero. Okay, so I won't prove that for you, but it's something you can see. Okay, so these are two lemmas about interchanging operations with trailing monomials. How can we use that to understand this? Okay, so we have a trailing monomial. We want to understand this thing. Right, and let's use these two lemmas to understand this. Well, what's the we have a multiplication here. What's the trailing monomial of this thing here? Right, it's just 1. Right, and what's the trailing monomial of this thing? It's the derivative of the trailing monomial. So this will equal 1 times the derivative of the trailing monomial. Okay, and so I think I'm going to do fast forward a couple steps, but basically what you end up showing using this is that the measure of a polynomial f is at least the dimension of the partial derivative space of the trailing monomial. Okay, because here we're taking partial derivatives of the trailing monomial, right? And so if you just iterate over all b, you get the partial derivative space of that trailing monomial. So what's happening here is that you have this measure, mu prime, And mu prime is defined with this, you multiply by something, and you have a derivative, and so on. And then we say that you can lower bound this measure of f by another measure associated to its trailing monomial. Okay, and that other measure was the measure we saw yesterday, which is just the space of all partial derivatives. And what we saw yesterday also is that this measure is at least 2 to the number of variables in this trailing monomial. Right? And so by combining it with this bound on our sparse polynomial, S is at least 2 to the number of variables in the trailing monomial. That exactly implies what we wanted. Okay. So I'm skipping a few steps here. You can verify them in the privacy of your own home, but where we all do our embarrassing calculations. But that's basically the result. Okay. So this is a very simple example of saying that you have some, simple algebraic computation, you translate it, and you make it even more simple in some way. And the number of translations that you need are small. Here you only needed one translation. In the next example, I want to do something more involved, and I'll be a little bit more hand-wavy. But are there any questions before I move on? Okay, so what I want to talk about now, what I want to talk about now is something called a commutative Reed-Once AVP. Okay, so yesterday we saw Reed-Once algebraic branching programs, and I defined them, and I'll define them again. But I want to talk about a subclass which captures a lot of interesting classes of computation, like depth repowering formulas and like sparse polynomials. And this is a so-called commutative case. Okay, so what is the definition here? Okay, suppose f of x, or that we're defining f of x is computable by a width w commutative Reed-Once AVP if what? Well, remember yesterday it was a commutable by Reed-Once AVP if you can say you take a bunch of matrices where each of them are univariate, you product them together, you take the 1-1 entry, that is f. Here we're going to basically do the same thing, except we're going to insist that the matrices are commutative. Okay, is that if f is expressible, you have a1 of x1 times ... you have an of xn. Yesterday I took the 1-1 entry. Today I'm just going to take the trace. Not really important. Okay, and ai of xi. What is this thing here? This is a polynomial. It's a univariate polynomial in the only variable xi, and it's a w by w matrix of such univariate polynomials. And I'm insisting here that all of the AIs commute. Okay, and what is the main example that we should remember? Like, what are the best examples of commutative matrices? Are when the AI are diagonal. Right, so they clearly commute if they're diagonal. And why am I focusing on this diagonal case? Is because in this case, this implies that f is a sum of products of univariates. Right, another way to write that would be that f is the summation of products of, basically you take the diagonal entries here, you have ai of xi, the jjth entry, j goes from 1 to w. Right, so these are w by w matrices. If they're all diagonal and you multiply them, what happens? Just the diagonal entries just multiply with each other. You take the trace, that's a summation operator. So what this is saying is you take these diagonal entries, the jj entries, you multiply them over all I, that's this multiplication here. The trace does the summation. Right? So in this particular commutative case, you get sums of products of univariates. And what we saw yesterday, sort of one someday, in Anken's talk, is that sums of powers of univariates, sums of powers of linear forms, can be expressed this way. It's also not too hard to see that sparse polynomials can be expressed this way. Okay, so this captures two different classes that we already talked about, and intuitively it captures other things, right? I guess provably it captures other things. Okay, but so we want to do PIT for this. We already saw PIT yesterday for the general Re1's ABP case, but I'm going to give you another proof. And the virtue of having many proofs is sometimes you can combine them in non-trivial ways and get something additionally new, but I won't show you that additionally new thing. Okay, so hopefully the definition is clear. What I want to show for you is vaguely argue the following theorem. So this is basically due to this Agrawal-Saha-Saxena paper. I'm using this language from the subsequent paper of myself, Ramsad and Amir, but basically all the ideas were there before. Okay, so suppose that you have F is a width W commutative Re1's ABP. Right, what we want to do is we want to translate it into something which has a low support monomial. Okay, and here's where we're going to use this generator idea. We're going to take F, and we're going to translate it by some generator g of y, and this is going to be in P of 2 log W. Okay, so W is the width. You take the log and you multiply by 2. That's the support of the monomial you're going to get. Okay, and the question is, how much randomness do I need to invest in this generator? Well, I'm not actually going to define it for you, unfortunately. But basically what you need here is that this is a 2 log W plus 1 wise independent map. So what do I mean by this? What I want is a generator such that when you look at any 2 log W plus 1 coordinates, that you can get anything that you want. Okay, so this is very analogous in Boolean pseudorandomness to like a k-wise independent probability distribution, right? You basically you restrict to any coordinates, and you get something which is really, really independent. Okay, and you can ask, well, how much randomness do I need to invest to get such a map? How many variables are there in W? I mean, intuitively, it's clear that you only need log W variables, order log W variables. Okay, so we're using, and the map will also be low degree. We're going to use a very simple generator, basically of logarithmic complexity. We translate it, and we get a monomial of logarithmic support, right? And then you apply the results that I erased to say that you get a hitting set. Okay, so this is what I kind of want to argue for today. Okay. So what we're going to do is we're going to use some of the same ideas that we saw yesterday with more ideas. But what was the key idea? The key definition was this definition of coefficient span, right? So suppose that you have f of x, right? This is going to be a w by w matrix valued polynomial, right? And we saw that you can express this as a polynomial with matrix coefficients, right? So each of these is a w by w matrix, right? The key definition was the coefficient span of this matrix valued polynomial is defined as the span of the coefficients, the span of these f's of a's, right? As you range over all a's, and this is contained in the space of all w by w matrices, right? So this is a vector space of dimension at most w squared. Okay, and just to explain why is it 2 log w, it's because it's log of w squared. No surprise there. Okay, good. Okay, the new definition for today is the definition of L concentration. Okay, so what's going on here? We have the span of the coefficients. We saw yesterday that the span of the coefficients is 0 if and only if the polynomial is 0. And what the Raj-Spilka algorithm does is it breaks the Re1's ABP into different parts. It sort of extracts out the coefficient span in some way, and then does some recursion. Okay, what we want to do today is we want to say that this is all about low support coefficients, coefficients of low support monomials. We want to say that the coefficient span is somehow related to the span not of all coefficients, but the span of coefficients just on those low support monomials. Okay, so what is the definition of L concentrated? We say that F is L concentrated if the coefficient span of F is equal to the span of the coefficients, but not necessarily all of them. We can restrict to those coefficients of monomials that involve at most L variables. Okay, so this is the 0 norm. Okay, so take those coefficients only on monomials involving few variables. That's also a vector space. We want to say that that actually captures the entire span of the coefficients. Okay, and so this could happen. It could not happen, right? But what we want to do is we want to translate into the situation where this happens. Now, just to have a small sanity check, right? this coefficient span is possibly of W squared dimension. Right? How many things are there here? Right? Well, let's just think about multilinear polynomials for a moment. How many possible coefficients are there here? And for multilinear polynomials, there would be something like n choose L. Right? And it could be hypothetically that, n is really small maybe or something. But the point is that if you want this span to be at least this size, it better be, to capture the entire coefficient span, it better be that n choose L is bigger than W squared. Because otherwise, there's just not enough vectors here to span the entire thing. Okay, so what this is suggesting is you could take something L like log W, maybe log W divided by log N, but log W will certainly give you this equality, assuming everything is correct. But basically, this is heuristically saying that you could expect something like log W. You're not going to expect constant concentration in particular. Okay, that's not going to happen. And you don't need things that are super large. You don't need W over 2 concentration. You can get something which is really small. So intuitively, you can take L to be very small. Okay, so this is concentration of the matrix thing, but we, in some sense, are really shooting for this polynomial. So how does that relate? Right, well, the lemma here is that if f of x is L concentrated, right, this is the matrix valued polynomial. What we really care about is trace. Then the trace of f is 0 if and only if, it's non-zero if and only if the trace of f of x is in P sub L. Okay, so you're saying, suppose your matrix value polynomial is L concentrated, then if the trace is non-zero, then it has a small support monomial. The other direction is sort of obvious. If it has a small support monomial, obviously it's non-zero. Okay, so what this is saying is that if we translate into L concentration, we get the small support monomial that we want, and then we can do PIT. Yeah, I mean, this is basically this thing. Good. Okay, so let's just focus on how do you get a small support monomial, or how do you translate into L concentration. Okay, so this is the main proposition. It's going to be a bit tough. It's tricky. The main thing we want to do here is we want a local to global phenomenon. Okay, so what does that mean? Right. My definition here is that you have a bunch of matrices, and you take their product, right, and then you take the trace. And we want this whole thing to be L concentrated. But the point is that because these matrices are commutative, you don't need to look at, you can sort of rearrange them for free, willy-nilly, right? And you can look at products of not just all the matrices, but of smaller matrices, smaller subsets of the matrices. Those are also polynomials that are related. And the question is, because they're smaller, there's subsets of products here, they involve fewer variables, and maybe we can translate those in this L concentration in an easier way. And the main point of this proposition is to say that if you can look at all small subcircuits, and all of those are L concentrated, then the entire product is L concentrated. So that's a bunch of words. Hopefully not too nonsensical, but let's make it a little bit precise here. Okay, so suppose that you have a1 of x1 up to an of xn, right? And these are commutative univariate matrix polynomials of size w by w. Right? Suppose that for any subset S of n, right? So there are n variables. For any subset S, and for all exponent vectors A, where the exponent vector involves L variables, we have the following fact. We have that you have concentration of the product of these matrices in S, that the coefficient of x to the A in the product AI of xi, where you're producting over things I and S, right? So this is like a subproduct of the entire commutative Riemann ABP. You take a coefficient only involving L variables. Suppose that this is contained in the span of the coefficients on L minus 1 variables. Okay, so you take a coefficient with respect to x to the b of the same product of the same thing, I and S, AI of xi. Right, so this is some span of coefficients, but I'm restricting the coefficients on L minus 1 variables. Okay, so it says, suppose that for all subcircuits of my commutative Riemann AVP, where the subcircuit, it's some product of the things, and I'm taking a coefficient on L variables, suppose these coefficients are contained in the span of coefficients on L minus 1 variables. Okay, so this is saying that this subcircuit has L minus 1 concentration, L minus 1 concentration in particular, right? But I'm only focusing on coefficients with respect to L things. So this is some sort of saying that this is L minus 1 concentrated. Suppose that was true. Then this implies that the same thing is true for all A. Okay, so let's just parse this for a sec. It's saying you look at this subcircuit, all of the subcircuits. If all of the subcircuits have L variable coefficients contained in the span of L minus 1 coefficients, then it's also true for all coefficients in L minus 1.
What's the quantifier on S?
Yeah, so for all S, let me rewrite this. So for all S, so here it says for all S and for all A at most L, you have L coefficients in L minus 1. Here you have for all S and for all A unrestricted, you have L coefficients contained in the span of, or all coefficients are in the span of L minus 1 coefficients. Which is in particular saying that you have L minus 1 concentration. Okay. All right, so this is a bit of a mouthful even to write out formally, so please, if there are any questions, let me know. Okay, so in this lemma is where we're really going to use the fact that the matrices commute. Because up till now, everything was sort of generic, right? Okay. So the way we're going to prove this is by induction. And the reason I wrote it out in this sort of weird quantifiers where you have for all S and whatever is to kind of make the induction less tricky, although it's still kind of tricky. Okay. So what we're going to do is we're going to induct on the number of variables in A. Right, so A is the coefficient I want to place in the span of the L minus 1 coefficients. Okay, so suppose this number is at most L. Okay, then it's done, right, because that's the hypothesis. Nothing too much going on there. Okay, suppose it's at least L. All right, so this is where we want to do something non-trivial. Basically, what we want to do is we want to, I think of it as a promotion argument. Okay, so this is saying you have some relation from L into L minus 1. What I want to do is I want to multiply both sides of this equation to relate L plus 1 to L. And then you have L plus 1 into L, L into L minus 1. Then you have L plus 1 into L minus 1. And then you keep on going. Okay, so let's just do it out in painfully detailed steps. Okay. So suppose you have a coefficient of x to the a, y to the b. Okay, so I've split my variables into x and y. So what I want to do, basically, I already understood coefficients with respect to x to the a, and I'm adding a new variable, right? So this is x to the a has, say, L things, or I'm going to induct on this, and I'm adding a new variable. Right? So you have coefficients of this monomial, and you have you want to look at, for some set, something like this. Sorry, and now what you're doing is you're adding a b of y. Right? Okay, so you have a set S, and then you're adding the new variable y. Right? We already understood everything without the y, and now we're adding in the y. That's our induction. Okay. The point here is that, just as before, we're really using variable disjointness. Right? We have x's and we have y's. This is a variable disjoint product. They're matrices, but it's still variable disjoint. So we can factor this. Right? So this is equal to the coefficient of x to the a of the product of the ai's times the coefficient of y to the b in b of y. Okay, so this is just using the variable disjointness in a super strong way. Okay, but now we have our induction hypothesis, right? X to the a involves fewer variables than this thing. I'm assuming b is like bigger than 1 or something, right? So this thing is in the span of the coefficients of say x to the c of this thing, of this product ai xi, right? Where here we're ranging over c of support at most L minus 1. Okay, so we did variables joint product, right? This thing is contained in the span of L minus 1 coefficients, but we have this other product. So we factored, now we're going to unfactor. What I want to do is I don't want to look at this entire span. Let's just look at a particular product because matrix products are bilinear, so it's enough to focus on a single C and combine it here. Okay, so let's look at the coefficient of x to the c in ai xi for ins times the coefficient of y to the b in by. Right, and we want to say that this particular coefficient is contained in L minus 1, and then we would apply it to the entire span here. So this is a variables joint product. We can undo the factorization. This is equal to the coefficient of x to the a, x to the c, x to the c, y to the b, product ins ai xi times b of y. Right, so we just use the variables joint thing to unfactor this. Okay. So I already used my induction hypothesis once, right? This expression was taking a coefficient of some number of variables fewer than the level of induction, so we can use our induction hypothesis here. Let's look at what's going on here, right? This product, you know, the reason I chose it over all subsets is because I'm really using subsets in different ways. But this is still a subcircuit of my original thing, right? So, but this coefficient, right? This is L minus 1 variables, right? This is a single variable. If you add them, it's L, right? So by my hypothesis, this is an L coefficient of some subset, right? So this should be in the span of the L minus 1, right? This is in the span of coefficients, say with respect to x to the e of my subcircuits like I and T or something, or blah. You have AI times B, where now these things are ranging over exponent vectors, which are at most L minus 1. Okay. So I claim that we're done, but let's remind ourselves why. Yes, I do, and that's a really subtle point, and let's dwell on that and understand why this is true. Okay, so we are using commutativity, and it's really subtle why we did that. Okay, so let's first understand why we're done, and then let's look at commutativity. Okay, so what do we want to prove? We wanted to prove that all of the coefficients of all of the subcircuits are contained in the span of the L minus 1 coefficients of those same subcircuits, right? We looked at a coefficient, we broke it into two parts where we have one monomial on a few variables, we have x, and then we have one more variable. We broke it apart, used our induction hypothesis once. So this is going from some number to basically L, because this is going to L minus 1. We multiply back, we have now a coefficient of just L. We apply our thing again, and this is the span of the coefficients on L minus 1 variables, right? And then because matrix product is bilinear, you have a span of a span, and span of a span is a span. Okay, so it is proving what we wanted. Why are we using commutativity? And this is kind of a subtle point. It's basically, the reason we're using commutativity is because B is on the right-hand side. It can be, but it doesn't have to be. Okay. The thing is that if you consider the map, A goes to A times B, like this is bilinear in B. Bilinear, linear in B. But consider the map AC goes to ABC. No. convinced myself last night, and okay, but basically,
I mean, I guess the point is when you are using the induction hypothesis on the A's,
yeah,
so the subcircuit, so for example, let's say A is 1, 2, and 3. Now the rank concentration could say that it's a span of 1, 2, 1, 3, and 2, 3.
yeah. Okay, so you have 1, 2, and 3.
But you're dropping one of the matrices in the middle, right? And you want to make sure that the coefficient spans are still well behaved. You want to write the coefficient span as a product of something in X and something in Y.
Right.
But if you drop something in the middle, then you might want to rearrange
Right.
things in order.
Right. And I think the point here is that what you're really looking is you want variable disjointness. Variable disjointness is what's allowing you to write to do this factorization. But if you had something like, you know, A of X, B of Y, C of X, and this wasn't C of Z, then you couldn't necessarily use variable disjointness to preserve the coefficient span independently. And so what you really need to do is you need to say that you can actually put C on the other side, you know, draw a line in the sand, and say you have something on the left, you have something on the right. And that is what allows you to preserve coefficient span independently, really using variable disjointness. And that's why you're using commutativity. It's a very subtle point. Yeah, but okay. But if you're not convinced, I can't convince you. So, okay. So what this shows is that if all of the subcircuits are L concentrated, then by the way, what time are we stopping? I feel like I've taken too much time already.
We started a bit late, and we have flexibility with the breaks.
Okay, 5 minutes. Yeah, 5 minutes is fine. So it says that if all of the small subcircuits are L concentrated, or L minus 1 concentrated, then you have the whole thing is L minus 1 concentrated. Okay. What we want to do now is we want to say that getting this first condition is cheap. Okay. So if we can get the first condition, we get the second condition. Second condition gives us this L support monomial. So we want to get the first condition cheaply. And so what's the theorem here? Suppose that f of x is a W by W matrix, right? It's W of matrix valued polynomials. Then suppose you translate x by a random alpha. The question is, what sort of concentration do we expect? Right? This is very analogous to the lemma that I erased a long time ago, which says if you have a random polynomial, right, you should expect a random translation to have a coefficient of support 1. Right? We shouldn't expect one concentration or two concentration here because of this argument, right? That there's simply not enough coefficients of low support to span the entire space. But if you have you could expect something like log W concentration because there are enough coefficients there. And this is exactly what this theorem is saying. Then this translated is 2 log W concentrated. Okay. So you translate by something random, you get 2 log W concentration. So this is a brute force statement, right? There's no complexity of F built in here, aside from the fact that it's a W by W matrix. But the point is that we're going to use this only brute force on small subcircuits because of this thing, right? So what is the right? How do we actually complete the statement? Well, let me just again. The intuition is that if you look at 2 log W, there are enough coefficients that this could possibly span this, and we live in the best of all possible worlds, so it's true. That's.
What's the quantifier on alpha?
Sorry. Oh yeah, random alpha. Right, so it's a random alpha, and obviously this is expensive if there's many variables, but let's just not do it with many variables. Okay, right, so, all right, so the corollary here is that suppose f of x is equal to the product of ai xi, where these are commutative. Right? What this implies is that suppose that you take f and you translate it by g of y, and this is 2 log w plus 1 independent. Right? You translate by this 2 log wy's independent map, then this entire matrix product is 2 log w concentrated. Okay. So just to review how this proof goes, It's basically following what we just did, right? Point is that g of y will induce 2 log W concentration in any small subcircuit, right? Any small subcircuit like product of AI xi, where I is in S and S is small. It's at most 2 log W. Okay. Basically, because of this theorem, you're looking at small subcircuits on small number of variables. If you look at any small number of variables of this output of this map, it's going to be fully independent, so you can use this. Okay, so this is saying that small sets have concentration. You can basically lift that immediately via bilinearity to this statement that you can look at, because the coefficients here are always touching very few variables. So again, you rearrange using commutativity to get this statement that all subcircuits have L and L minus 1. Okay, so all the small subcircuits are concentrated, and then the second step is to lift to 2 log W concentration of the entire thing using this local to global phenomenon. Okay, so you've translated in a 2 log W concentration. Then you can use the fact that the trace now has a small support monomial if it's on few variables. If it's non-zero, it has a small support monomial. Then you use PIT. What is the ultimate corollary? Right, is basically that you get a polynomial to the log W size hitting Z for these commutative V1CDPs. Okay, which is what I wanted to prove. Okay, so let's just say one more time, because this is obviously a lot of sequence of non-trivial ideas, right? What it's saying is that you have a non-commutative V1CDP. You can define coefficient span. And we saw yesterday that you can use variable disjointness to sort of independently preserve coefficient span. What we want to do today is to look at low support monomials. And the key definition here is this L concentration, saying that the low support monomials, they're also matrices, span all of the other coefficients, right? And we can expect that maybe the log W support coefficients can do this just because of counting reasons. And this theorem is saying that if you do a random translation, they will actually span. Okay, but this is sort of brute force. We need to apply it in a judicious way to get something that's non-trivial. Right, this thing is saying L concentration will imply that the monomial has a low support monomial, which is that the trace has a low support monomial, which gives you your PIT. Here we have this local global phenomenon. And, I mean, it's a bit of a mouthful, but the main idea is that as I sort of said, is that this is saying if you can take L to L minus 1, variable disjointness will give you L into L plus 1, or will give you L plus 1 to L. And this is the step where we're really using commutativity. And then you just say, well, L plus 1 goes to L goes to L minus 1, so L plus 1 goes to L minus 1. And then you just keep on going. And then you get everything into L minus 1. And so if you shift then, or translate, by a map with only logarithmic amount of independence, all of the subcircuits will be concentrated, and then this local global phenomenon will give you what you want. Okay, thank you.
I guess one thing you haven't shown is how to move from small sets S to the entire.
Yeah, I didn't. That is an omission. Yes, basically, you basically use variable disjointness. Basically, that if you have a small set and you want to go to a large set, the point is that if you have a coefficient, this coefficient here in my hypothesis only touches L variables. So I can look at the set associated with those all the L variables and put the other variables outside. Because of variable disjointness, this is logic. This is fine, and you can multiply the other variables on both sides of the equation. So that's how you get from this statement to this statement.